Let us look into the PNR flow in the physical design process. Place and route is the second step followed by the synthesis. So what are the synthesis outputs that we have acquired? One is gate level netlist, other one is HDC constraints file for timing. So we use these outputs from the synthesis and we give it to the inputs for the entire place and route flow in the physical design process. So place and route starts with the stages like data preparation and end till routing. What are the different stages involved in place and route in the physical design process or PNR? They are the various different processes or stages involved in the physical design process of a block or a chip are data preparation, power plan, data preparation, floor plan, power plan, placement, CTS, and then routing. So there are two other input files or input scripts that are required for defining the multi-scenarios of functionality of the design and some setup file required for accessing the libraries and technologies to the design. Let us go through each individual Tcl file and execute the Tcl file to complete the stages of the physical design process. Now we are looking into the each Tcl file and then we will be executing the Tcl file as we have done for the design compiler Tcl scripting for the synthesis process to be completed. So for this place and route, we are starting with data preparation as the first step. For completing the place and route, we need to invoke the tool called ICC Compiler by the Synopsys organization. So ICC-II shell is the design tool for completing the process of physical design. Like we have used design compiler, that is DC_shell for synthesis. Likewise, we are using ICC-II shell for place and route. So to invoke this ICC-II_shell, we need to enable this shell and then we can invoke the tool by ICC-II_shell command. After this, the tool will be loaded in this way. Now you are in the shell domain and you can use the shell interface for doing things. So for this, you can run the Tcl scripts by sourcing the files. Before sourcing it, let us look into the data preparation.tcl. This is the data preparation.tcl. So in this Tcl file, we can see different set of commands executing from common setup.tcl file till the saving of the block. So in between, in this data preparation stage, our main motto is to load the input files, namely library files, tech files, which is technology files, and RC related files, which are nothing but table lookup plus file. Library files are nothing but getting the link library and target library from this command set. These are the Tcl commands: set, create lib, read verilog, and every sentence of the command starts with the Tcl command. You can see now we are loading the link libraries and the required reference libraries for the technology that we want to incorporate for the counter.top v. This counter of v is the output gate level netlist file that is generated from the synthesis process, which is stored in the outputs directory of the synthesis process. So in such a way, we are reading the verilog in the second step. After loading the libraries, we are reading through the verilog design, and after reading verilog, the current design is set as up-down counter. So this is the flow of data preparation, which requires loading of input files and getting the output DB, which is database, ready for the remaining stages of the physical design process. So data preparation follows with floor plan, and floor plan follows with power plan, and that flow goes on till routing. This is the flow, and each one of these are called stages. Let us look into the executing of this data preparation script file. There are two ways of executing this file. You can run each line, copying this line into the command prompt, or you can execute the Tcl file in two ways. Either you can copy each line as each individual command by doing right click on it and clicking copy, and then you can go to the terminal window and there you can paste. Or else the second way of doing the execution of a Tcl file is nothing but going to the terminal window and entering the command line source -e -v and expressing the path or the path of the directory where you can find the data preparation.tcl file, and then if you can press enter, the entire stages in the data preparation flow will be executed. Ignore some of the warnings where those warnings will be understood by you by the entire training. Ideally, each stage would take amount of time from 15 to 20 minutes. But few of the optimization steps might take much longer. So now we have successfully completed the data preparation stage by executing all the lines of commands in the Tcl file with one source command. Likewise, we can execute source command for each of the stages Tcl file. Like for data preparation, we can make it for floor plan, or we can do it for next stage is power plan, or we can go till routing. But before doing all the executions in one go, let us check for the each stage's Tcl file. Now let me allow to open the Tcl file of floor plan. Floor planning is the stage where you can relate with the construction of a building in such a way that every design requires a layout or the architecture of layout where you need to place the things. So this is a blueprint that we are creating for placing the macros or cells or ports or any wires to be connected. So this is the floor plan Tcl which involves only basic commands that are needed for the small design called counter.v that we are working on. Initially, before going to the floor plan stage, we go through the sanity checks. Sanity checks is nothing but getting assurance of the layout that you are placing things has no constraints or no any previous designs or no any timing related issues in the same layout. Ensuring the layout is clean gives us the confidence to go further for floor planning design. So now you have seen the floor plan Tcl which is going to place the pins by itself and also getting the status of the ports that are placed. So pins are nothing but ports in some scenarios. And then we can open the GUI and we can see what layout do we need to create. So in this we might involve graphic user interface again for understanding the boundaries of die and core and placing the cells in that. Before placing, the entire step is called floor plan for architecture level designs. Let us go back to the ICC-II shell and try to open the GUI. GUI is a graphic user interface which is a window from the Synopsys which can show you the actual layout and layers in the visible manner. And this window is nothing but a terminal or the shell scripting domain. But now we are trying to open the graphic user interface. Command is start_GUI. Now you can see what are all the cells that are present in our layout. So to initialize the floor plan, we can go for task in the toolbar and we can go for design planning. Double click on it and you can see the right window which is opening the design planning overview. In this right side window, you can see the floor plan preparation. And then you can understand each stages in the floor planning and you can read through it. Now let us fix the die area and core area for our design requirements. Ideally, the core utilization inside the floor planning is defined by the tool itself as 0.7 or 70% utilization that we call. And we maintain aspect ratio as 1 for ideal situations. These sides are nothing but the design which we are designing requires a length and breadth of it. So if we are considering A as the length and B as the breadth of the side of a square diagram or a rectangular shape, we can give the values as per our requirements. Let us take the values as 5 and 5 for the die area, and you can maintain the uniformity as 0.5. Those are the basic values that you can give, and you can preview always of the design. Now let us go on to core area, and you can maintain the same values for here itself, and then you can click on preview and press apply. Now in the bigger window you can see two different variations of the box. This is the entire die area. The outer box represents the die area and the closer ones in the inside requires the core area. So this is the core area where we are going to place the cells, routing nets and all. Let us come back to our terminal window and try to run the GUI. And now we can source the Tcl file. For sourcing or executing the Tcl file of the floor plan is the same with the data preparation source execution command. Now you can see in our library we have saved our blocks of each stage as blocks as design import done or import underscore done, that is nothing but data preparation stage, and then we are moving on to the floor plan done. After every stage completed successfully, we can save the block as floor plan done or import underscore done or power plan underscore done likewise. So that command is save block as floor plan done. This is there in the script file. So now let us move on to another stage of place and route, which is nothing but power plan, and that can be observed in the powerplan.tcl scripting. Powerplan is a stage where you need to connect the power and ground ports or power and ground nets throughout the entire design of a block or a full chip. Now you can see the commands of Powerplanning Tcl file, which is used for power planning stage in the physical design process. The first step is creating the PG nets, and the second one is making logical connections for the created PG nets. So create and connect, those are the second step. And third step you can see setting up the attributes for required tie cells. Tie cells are nothing but physical cells used for making the connections of NMOS and PMOS or VDD and VSS. VSS is nothing but ground and VDD is nothing but power. That we are declaring these things as nets. And in the power routing, we also create PG rails for making the metal layers working on it or going throughout the rails. Rails are just reference points, and thus we are declaring horizontal layer M9 and vertical layer M8 to be understood inside the layers of PG mesh pattern. Mesh and rails are interrelated for the power routing or power planning. Now in the last stages, we go through the creating of standard cell rails and creating vias between rails. Vias are the alternative pinning points between horizontal and vertical metal layers for the VDD and VSS strips to avoid some of the floating wires or floating nets. There are many more uses and advantages of creating vias. These vias are created by the tool by the command by create PG vias. Now after creation of all these things, we go for checking or verifications. So checking PG connectivity and checking PG DRC. This check PG DRC gives us a good image of nets which are open or which are short. There might be some errors which we call DRC errors, in which include shorts and opens, and some other errors. Shorts are nothing but two metal layers touching that can be caused by electromigration or some other applications. And with the opens, we have floating wires which are called as open nets, and those errors will be understood by the check pgdrc, and we can fix these errors in the later stages, but not here. We are just focusing on designing and developing. The error rectification and error reductions are done in the later stages of the physical design process. After completing this entire process of creation, we go through the save block as Powerplan done. Now let us execute the command for Powerplan done. As you can see, I am using the source -e-v command for all the Tcl scripts to be executing. Or else you can also follow another step by copying each line of the Tcl file and pasting it in the terminal window, and then you can execute. Either you can run the entire Tcl file or you can run one command of the Tcl file, one at a time. As you can see, this design is done. Now whenever we notice save block as Powerplan done and we get the 1 here, then the execution is successfully completed. Now for verification, we can do list underscore blocks, and then we can notice now we are having Powerplan done. Earlier this was not present. Now let us move on to the next stage called placement. Placement is nothing but placing of cells which are required for the design, which also act as connectivity between macros and ports. Allow me to open you the Tcl file of placement.tcl. A gentle reminder, these placement, Powerplan, Floorplan or any other stages Tcl file are present in the scripts folder of every project. This is the Tcl file that it is made for executing the placement of cells and placement of macros and placing the blockages between macros. Blockages are nothing but a restriction between two macros or in the open channel space for restricting the cells to be placed in between macros or in the crucial channel spacing or routing. So in this placement, we are going to group the paths which are from macro to reg or reg to macro or inputs to reg or outputs to reg to reg, and then we go for pre-placement checks with the check design command, which gives the idea of any errors that are required to be reduced before going to the placement, or any warnings that we can ignore before going to the placement stage. And there are few other commands that we are going to place in the placement preparation. And in the placement, we are going to set app options for place course congestion driven max utilization value of 0.6. So this is like utilization of the cells is declared in this command as 0.6, as we have declared core utilization as 0.7. So as it is maximum, only the tool will take whichever value it is required for the size of the design. So then we analyze and then create placement. Like this way, after executing all these commands, we go to the optimization stage where it starts from place opt to the final opto. It is a command starting from checking the entire design and ending till the optimization is required. That is called place opt to the final opto. After optimization, we do check the timing reports and then utilization is reported and we go through the reports of the utilization. Then connect the PG nets whenever it is required. If any other cells are left over, we can connect those cells with the PG nets by connect PG net, as we have done in this power plant stage. So now we can save block as placement done. We can open the terminal and we can see the placement of cells in this manner by sourcing and executing. Before executing this, let us check the power plan done graphic user interface and how our design is developed there after floor plan is done. So let us open the graphic user interface window to check the power routing rails and nets. As you can see, this is the VDD, and allow me to zoom, and you can see the names which is having VDD, VSS and VIA. This part is called VIA. VIA is pinning between a vertical and horizontal metal layers for VDD and VSS strips in an alternative manner. So as you can see, there are two stripes for VSS and VDD, and VDD followed by VDD again. This is an alternative way of arranging things. And you can see these are the ports that we are going to look at, input and output. And all the metal layers are evenly distributed in between the stages, and some are used in floor planning and some are used in power planning and some other are used in placement, and some leftover are used in CTS and routing. Some metal layers like M6 and M8 are used in CTS, or M9 and M7 are used in routing, or some other things are used in placement or power plant stages. So now after power plan, we have used two metal layers like this. One metal layer used for VSS, that is ground, is M1 in the horizontal, and the other metal layer used for power is nothing but VDD. In the left bottom corner, you can observe which layer is used for which type of the power net. Now come back to the terminal window and let us execute the placement.tcl for completion of placement stage in the physical design process. Now we can check the number of blocks present in the current directory or current design or current library. We can check placement done is saved. So go back to the GUI by executing the command start _ GUI to check the graphic user interface window how the cells are placed. So previously the cells are outside the boundary and now the cells are placed inside the boundary. If we zoom into one of the cells and then we can observe what this cell is looking like. To observe in detail, select any of the cell. Select any of the cell, and in the objects window in the view settings in the right side terminal, you can enable different objects of the same cell, and then you can observe what it is. So you can enable pins, and when you enable the pins, these pins will show the power and ground ports of the or input and output ports of the cell. So let us zoom into the two ports for the same cell. You can see the output port is named after the O, and the input port is named after I. So the overall image looks like this, and whenever you want to stop viewing these pins and all, you can disable it again. Now this is the image, and if you want to disable all the metal layers that were assigned in the Powerplanning, that you can ignore them by disabling all the metal layers from layers window. Here you can see the cells are placed inside the core and the ports are placed nearby the core. Let us enable all the metal layers. So that we can conclude the placement done is saved after executing the placement.tcl. Let us move on to the next stage, which is nothing but clock tree synthesis. Before going there, let us check through the clock tree synthesis tcl file for the better understanding. So this is the CTS tcl file, which has everything related to the timing constraints for the entire design and which metal layers to be used for the timing. We can say M6 and M7 are used for routing layers for clock signals. After connecting them with the VDD and VSS, we can report the different types of reports like constraints, clock tree options, quality of the reports, and delay types min and max. Delay type minimum is nothing but hold violations can be checked with the report timing, and max delay type gives us the setup timing violations in the report timing. After executing all the commands, you can save the block as CTS10. Now without any delay, let us go on to the terminal and try to execute the cts.tcl file. Now after the completion of CTS is done, we can verify the list of blocks entered here. So that we have CTS done, and in this block we can go further with the routing stage, and in the routing we can check the routing tcl file and then come back to the execution of the tcl file. So this is the tcl file that we are going to execute for routing stage. Routing stage is nothing but having all the tracks between macros or cells in between ports to connect the interface between the neighboring blocks or inside the block. Inside the block, cells and macros can be connected with the tracks and routing nets. Here we are declaring M7 as the maximum routing layer and M2 as the minimum routing layer, and that we are ignoring after declaration. And in such a way, there should be no crosstalk or delay calculations. A delay in the routing happened in the routing block. For that reasons, we are setting app options as for the timing relation to the design. Then after, we route the tracks as per global routing and track routing or the detail routing. And these three steps can be combinedly done by the command root underscore auto. Let us execute this command and then we can save the block as root done. As you can see, this routing done is saved as root done db after the execution of routing optimization and routing script. So now to verify if we can execute the command list underscore blocks, we can check the root done db is done. So this is how entire place and route process is happening in the physical design flow. Let us go through the GUI and check the routing happened. Now you can see the entire layout is optimized and design has occurred in this way. All the metal layers you can disable once and you can see the only placement of cells. But now if you want to enable each metal layer, you can check by each individual metal layer in the right side layers window. Let us go and check the M1, M2, M3 and M4 metal layers. So in this way you can enable all the metal layers in the layout window. Graphic user interface is usually used for analyzing and correcting the metal layers. So this is the entire physical design flow for a counter.v for this design. Now this is the schematic view of the up-down counter as we have verified in the synthesis stage. If you want to see deep inside the up-down counter, you can observe the cells that are present here. This is the layout window. And now you can see the optimized design which is compared to the original RTL flow. And you can also observe placing of the necessary cells for any timing related issues to be solved. So we can exit the design by stopping the GUI with the command stop GUI. And we can exit the tool ICC-II shell by the command exit. And that throws us to the same directory that we have invoked the tool. This is the completed DB for the entire design. Thank you.